I want to explain why a traveling wave is expressed in terms of this equation. Y of xt equals a cosine of kx minus wt. Right? So at first, it's kind of like random because like you think about a traveling wave, it travels both in the space and in time. And like a lot of people, like when I first learned this, I just kind of like took it for granted. I didn't really think about this a lot, but then like I kind of like stared at it and I found it really suspicious. So I looked into it, like I really thought about it, right? So like how do I make sense of it? So let's start without thinking about time. Let's just think about space, right? So if we have just travel a wave traveling through space. So let's think about a sinusoidal wave, right? Like a sine wave, for example, or a cosine wave. Let's do a cosine wave. So the cosine wave is just kind of like that, right? Right, in terms of the space. So then this is the amplitude. So we all know this is the amplitude, that's the wave number. So A makes it like bigger or like this is like kind of like the amplitude, right? So A changes like how big, K changes like how close they are. So the bigger the K, right, that means like cosine kind of reacts kind of the effect is like bigger, because like if K is bigger, that means like you increase x by a little bit, right? Kx becomes like changed by a whole lot. So then cosine of kx is just like reacts like so kind of like you think about it, like you're speeding up the effect of the cosine function. So the bigger the k, right, then the closer together. So basically cosine, I think of cosine as like you take a x, right? You take x as like a straight line. Cosine kind of is like a force that kind of like shifts it up and down, up and down, like the kind of like that. So then if you have a more stronger, so I think about like k here as like it's like emphasizing or like making the effect of cosine function stronger. So the cosine kind of like do like more. So if you increase k, kind of like closer, like the distance here gets like smaller. So you think about, so this represents like a one direction, you know, just a wave. If you look at it sideways, just kind of like a plane, like a wave, kind of like going up and down. So this is y of x, right? So then if you want to express like a wave, not just like as if like you kind of stop time, this is no time, right? Y of x, you kind of stop time, you just like kind of look at the wave as if you're like stop time, and like, you know, time is frozen, everything's frozen except for you, and you're kind of like moving yourself through the space to look at the wave like up and down, right? So that's what it looks like. But then if you want to add in the time factor, which is like, okay, what does this wave look like say like 5 seconds ago or like 10 seconds ago? Like how do I know what happens in the past or the future, right? So you kind of like pause time, and what does that look like? So we want to add in the time factor. So before we do that, right, we want to think about we kind of want to think about something. We start with something simpler, right? So if we just have a point in space and time, so let's say we have a point here, like x and t, right? This point, right? Let's say that this point, we know that it keeps moving to some like direction at velocity v. So v, a velocity, right, has like speed and direction. So it moves like v somewhere, right? So like then we know exactly, like we know where it's at, like at time 0. So this is time t. So x and t are both like some variable, you know, some x, some t. So we know exactly where this point is at time 0. Why is that? Because we know exactly how fast it moves, right? So then at time t equals 0, it's at x minus vt, right? This we agree, right? Because like x minus vt at time 0, at time t, it moved right vt into xt. So this makes intuitive, very simple. So then let's think about it, right? So what would it be like for a wave in this situation? So we know that, like, we know a wave, okay? So we kind of said like just like yx equals this, right? But then we can also say, okay, let's just call this time t. I give a kind of like a coordinate in time. So we say, okay, so this time t is equal to a cosine of kx. Right. So basically, we just put it like we take this wave that's frozen in space and time, and we call that time in space the time 0. So we kind of just label. We didn't do anything here, anything new here. So we just say, okay, at x and time equals 0, it's a cosine kx. Nothing new, right? All right. And now we want to know how do we express this, like, in terms like we change time. Like we don't just fix the time as t equals 0. We actually change time. So we want the time to be a variable as well. So what would the time be? So if we say, what is the expression y, x, and t? So then we know here y of x and t. So that means like this it's equal to y of x minus vt, 0. Right, so we said these are the same, right? So any single point, like this transformation holds true. So that we can say, we already know this expression is for time x 0, right? So then we already know this expression is for anything at time 0. So then we just like we plug this part into that x, and we get a cosine of k of x minus vt. Right? So then we kind of expand this, we would get a cosine of kx minus kvt. And kv here is just omega. So then we have a cosine of kx minus omega t. So this is exactly how we express a wave that's traveling both in space and in time. And that's why these two things are both going inside of the cosine function. I hope that was clear.